a postdoc now in Saclay. He started right now to work in the Louail project with the group there. But before he was a PhD student in geography cities lab in University of Louail. He did the PhD with Denis Kuman. And then after that he moved to Toulouse for doing a postdoc about modeling water systems. Well, I mean, more. Thank you for coming and welcome.
Thanks, José, for the presentation. So hello to everybody, and thanks for being here. So that what I'm going to talk is the volume is good. You hear me fine? What I'm going to talk about today is some related to some work I did during my PhD thesis, and is concerned with that's an attempt, in fact, to model in the long run the evolution of European of cities of the world, and focus on the comparison between the evolution of the spatial organization of cities in Europe and in the US. Okay. So the title of my presentation is exploring the effects of street networks on urban forms. Since what I will present is an attempt to see if finally the shapes of the street networks are sufficient enough for explaining the kind of very different kind of patterns you can observe. Well, in fact, these are extreme cases. Like here, you have the footprint of Atlanta in the US, and here Barcelona. So those are two cities with the same number of inhabitants. But when I said those are extreme cases, not all the cities exhibit some same kind of extreme patterns. But so the idea of this presentation is to see to what extent the networks can be responsible to the more executive forms of repartition patterns we observe in universities. So let's say a few words about the background and the positioning of my work. So what I'm going to present is a part of a project which is a long-run project which is called simpop, and you will find a website easily in Google. And the simpop project is in fact an attempt to try to give a computational traduction with the help of multi-agent systems to a geographical evolutionary theory, which has been mainly set up by Denis Kuman's team in Paris for the last 30 years. And so this urban theory proposed to apprehend urban systems as complex systems, in fact, but with the particularity that the systems are historical systems. So they are they exhibit some generic properties and some generic universal laws, like for example the well-known Z-flow, the rank size organization of urban systems all over the world, and some more specific patterns related to their specific history and historical events that happen in history. So in this lab, Geographicité, in fact, this lab was founded in the beginning of the 80s, and people there are quantitatively studying the urban systems through a set of methods, which first of them is maybe to try to, in order to compare cities of the world upon a significative basis, try to build some harmonized urban database, which goes beyond sometimes arbitrary delimitation of the cities by national census. So create some delimitations of cities which are based on morphological or functional aspects. They do a lot of statistics, and part of the methods used there are computer simulation. So in this urban evolutionary theory, as I told you, there is a different level of organizations that can be distinguished. One of them is maybe the most obvious for us is the level of a city, isolated from the others. But at another scale, there is also some high regularity stories and properties at the level of what geographers call the systems of cities, which are in fact networks of cities that don't evolve independently and which are depending from one another. Okay. But the level on which I'm going to focus during this presentation is the level of cities. I just mentioned this level because many works have been done at these spatial scales during the last 30 years. Okay, so if we focus on European and American cities, we can observe some we can observe different kind of differences, and I will try to list some of them. So, for example, when we focus on the footprints, the spatial, let's say, inscription of the cities on the territory, you can observe some globally some more diluted patterns in the US. Like, for example, here you have histograms of densities as a function of the distance to the historical centers. And so what you see is that, those are three European cities and three American cities. And you observe typically a gradient, which is really more intense in the case of European cities. So over the...
I understand what you understand by footprints. You are plotting densities. What? Of people, of edifications?
Yeah, densities of population.
Population density.
Resident population.
Okay.
I'm sorry. And so these kind of patterns, in fact, they were indisputable until, let's say, the beginning of the 90s. In the last 20 years, we see some more complicated and entangled forms of morphological forms appearing with a lot of polycentrism appearing also in European cities. But if you compare these forms on the long run, let's say in periods of several centuries since the beginning of localizations, you can observe some really more centralized forms of city repartitions in European cities compared to US ones. Okay, so this is for example, typical illustration I showed you during my first slide. So these are the footprints of Untitled Barcelona. So globally, since we are talking about cities of the same approach, so when we compare cities of the same size of population, if you have a gradient which is stronger in the European cities, necessarily you have some cities which are more space consuming in the US. Another kind of differences that we can observe also is often the shapes of the street networks. Here also these are kind of typical cases. So here you have the street network of Milan in Italy, and here you have Phoenix in Brazil. So those are not always as systematic, since in fact you have, for example, parts of European cities, full neighborhoods where you have some grid forms too, and at the same time in the US you have also some big radials, but in a general manner, you have some more radio concentric forms of street networks in Europe because of the period in which the cities have been built, where generally you have some circular rings around the center, which correspond to the successive walls of the cities, which have been broken to extend the city. And in the US, and particularly in the west side, west part of the US, you have lots of grids because of the cities were often built contemporary to the use to the development of car. Okay. So another consequence of that is that so the first consequence is that for the modeling works that in which we are interested, we will do the hypothesis that a monocentric framework is relevant to model the evolution of these cities over a 2-century period. Another difference that in the cities are the average speeds we can observe in the core of these cities, in the centers of these cities. And so, for example, here you have a comparison of studies that has been run on 28 US metropolitan cities, computing the average speed in the center of the cities. And here, for example, the speed of Paris, which is comparable to other cities in Europe. And so you see there is a 1.5 approximately ratio in the speeds of commuters inside the cities. Okay. So another strong hypothesis is that given the lack of data that we have about the average speed of commuting inside the European cities, we're going to take for our modeling work some average profile of 1.5 ratio between speeds in the US and European cities. A third differences between US and European cities lies in the spatial repartition of both densities and prices. Okay, so that's what I show you with a graph of issued from work of Almato. So one explanation of that is that given to the relativity, European cities in fact are much more older than US ones. So from a symbolic perspective and value perspective, you have much more accumulated values in the center of European cities compared to US ones. And there is also, maybe we should mention some cultural differences, since, for example, contemporary to their edifications, there is also maybe a trend in the US culture of defiance toward living in the cities with important aspect of having its own personal house in the suburbs of the cities, which could explain why also the centers of the cities were less densified. Okay, so when you take a look also at the curve, the evolution of the rent prices with distance to the center, you also have some gradients which are more important in the European cities. And so I will finish this set of observation with this plot of issue from a paper from Vato also, which gives you the average population densities for many cities of the world, and they are colored by a continent of apartments. So you see there are clearly some families with Asian cities which are really more dense than US ones. Okay. And the European ones in the middle, they are in fact like an average kind of ones. Okay. So I show you several differences, some geometrical differences, split networks and speed differences. I also show you that there are some more spatial repartition differences. And so my question was, is it possible to, well, in fact, is there some kind of universal generic processes which correspond to how people locate in space, how they choose their location, how enterprise choose their location in the urban space? Are these processes universal? And finally, which explain why there are some more diluted forms and more sprawling in the US cities compared to European ones? Is it only finally a matter of networks and speeds? And so finally, could we have a model which will be the same for both sets of cities, but which, when executed on different kinds of networks and speeds, will generate some patterns of densities and rent prices repartition, which will be different. And the period to consider, since we are interested in the morphogenesis of these systems, is necessarily a long-term period. We cannot only focus on the last 20 or 30 years. We have to take into account the evolution of the speed networks through time, and of the speed of the transport networks through time, etc. Okay. So maybe I will speak kind of quickly on that, since you are it's nothing new to you as a physicist. So maybe one thing to notice is that since we want to we are interested in the morphogenesis of these cities. So we are not only interested in reproducing a typical pattern for given situation, but more like a coherent temporal and spatial evolution of the cities. So what we have to do, in fact, is modeling an historical system. And when you're concerned with social systems, you cannot just practice some, let's say, from scratch simulation where you will just define an additional state and set the parameters values and then run your system and just let it run during the whole period of 2 centuries. Given the particular historical evolution of the systems and all the things that you have to take into account to reproduce coherently their total amount of population. For example, you have to take into account historical events like wars or stuff like that. So, for example, you have to inject at each time of the evolution of your system some parameter values that are in fact temporalized. It's not just setting up an initial value. You have to feed your simulated systems with controlling parameters through the different steps of its evolution. So geographers call that historical data-driven simulations to insist on the fact that if you want to coherently reproduce your historical trajectory, you have to take into account all these historical parameters. Another thing from a methodological point of view, which is to be considered, is once again the fact that we're interested in the evolution of a trajectory of a human system. So we're interested in the successive steps and compare at each of the development with the simulated system with some available historical data. So one of given this project of modeling the evolution of a city over a 200 years period, it raises several modeling difficulties. One of the first of them is maybe to the question of how we represent spatially the evolution of the space inside the city for 200 year periods. So in urban simulation, the main trend is to integrate really precise data coming from GIS, since something like 20 years we have a lot of GIS data for many cities of the world. But the thing is that on this historical period, it's maybe not that relevant, since once again we don't have this kind of geometrical data for an ancient period of times. And what we want to simulate finally are really, what I explained to you is that we want to simulate some more repartition patterns and stylized facts and related to densities repartitions and not finally the geometrical evolution of the shapes of the neighborhoods of the cities or the inner parts of the city. So our solution is finally to adopt a graph-based representation of city space, okay, not a geometrical representation. And to differentiate the different part of the city space, we weight each vertex of the graph by some accessibility indexes, which traduce how much this node in the graph is accessible compared to others. So to compute relevant accessibility indexes through time, we have to take into account the evolution of speeds on these networks. So this is done by supposing given to geographers that, for example, from the beginnings of the 19th century to the end, the main part of the commuting travels were done by foot. So you suppose, for example, an average speed of 5 kilometers, and then when the car arrived at the beginning of the 20s, and you increase the speed, etc. And so this gives you some weighted graphs, differently weighted graphs for these different moments of the evolution of your system. Another difficulty when you want to model a city over a 200 years period of time is what kind of processes you're going to integrate through that, given that there are at least many processes that could be taken into account. So generally speaking, when economists, for example, do some locational modeling inside the cities, focus on periods of time which are shorter and for which, for example, it is more relevant to take into account a typical classification of firms and businesses and simulate different kind of strategy for this kind of businesses. But for 2,000 years period, it's maybe more complicated. So for this period, we decided to adopt an original approach in locational theory, where what we're going to localize inside the cities, in fact, are what geographers call urban functions, and which are some geographical objects, or let's say concepts, that make sense when you compare the evolution of urban systems over long periods of time. And let's imagine that, for example, one urban function, here you have the list of urban functions, so these are some central ones, some cyclic ones, and each cycle, for example, corresponds to a cycle of innovations. So in the, I don't know if you heard about the theory of innovation size scale of Schumpeter or economics like that. And innovation cycles, they regroup some activities that have been contemporary to the same period of technological evolutions and that have been a shift towards the economic evolution. So, for example, cycle 1 will be large-scale maritime trades. Cycle 2 will be activities related to first industrial revolutions. Cycle 3 will be the automobile revolution, and cycle 4 will be stick and information stick. So once you have a kind of aggregation of these activities and the weight of each of these urban functions at different periods of time, you can have some kinds of average profile of which is dominant at each period of time. And so what you localize inside the city, in fact, these are not business or firms, but more these kinds of aggregated conceptual actors which gather a lot of enterprise, business, firms, etc. Okay, so this may seem obscure and to you. So here, for example, I mentioned some name of people working on that concept and theorizing it. So an important thing to say is that when we compute this kind of profiles of a temporal evolution of an average European city, of an average US cities, and its functional profile, we apply this kind of serialized profile on harmonized urban database. Okay, so this is important.
But what are you using this for? This is information about how fast people is going to travel, or
no. In fact, these are an average curve. For example, this is a curve of population we're gonna inject in the model as the population to locate, okay, in the city, and these are the repartition of this population to locate inside different class of let's say professional activity. Okay. With these activities having different logic of localization in the urban space. Since, for example, dominant innovative activities, they don't have the same economic possibilities to locate in the urban space, and they're not going to look for the same kind of synergetic logics to locate inside the urban space. Okay? For example, you know that industries, for example, they cluster a lot more than, for example, activities which are common, like, I don't know, all activities that you find in every city's central place activities, like schools or universities or commerce. So these typologies, aggregated typologies, which are maybe very abstract, but in the same time which are the only one which are relevant over periods of several centuries, periods of times. allows to define some profiles of populations separated by different class of activities that you inject inside your location model. And what you're going to try to find finally is that given some different class of urban functions, some number of people to locate, some a certain amount of money to locate them into the urban space. Okay, so you have some innovative innovative functions, some central place functions, and administrative functions, some residential functions. What you're going to try is to find some, to test some location theory models to model these functions inside the urban space, given different street networks and different morphology of cities, and see what it gives as a result. Okay. So I'm gonna skip. Yeah. Okay. So that's the idea of our modeling approach is to model in fact localization processes of this urban function inside the city, and try to find a kind of minimal set of rules that will generate some well-differentiated spatial repartitions depending on the geometry in which these rules are executed. So this is the model. His name is simpopNano. And the rules inside are location rules. The parameters are geometries of street networks, including the topology of the networks and the speeds. And what you put as the inputs are profiles of your urban functions to localize over these two century periods of time. And what you look at as outputs are these indicators of spatial repartitions of density, prices, and activities. This is agent-based modeling. So let's say we are not always restraining ourselves to rules that we can track analytically. And so for some of them, there are really there are no other way to study them than to compute them. So to give you I'm sorry for this graph, it is in French in fact. The word, but I think you can infer what the image is basically. Okay, the main idea of this model is that you have several components that are in bold. Okay, and for each of these components, this is a rule in fact, and for each of this rule, we took some models of the literature of spatial economy to try different combination of instance of rules. So, for example, this rule is going to give you the evolution of the accessibility of the different parts of the city. So this is mainly about. I showed you the graph with different nodes and different values of accessibility indicators. This rule is mainly concerned with changing the weight of these nodes through time. This gives you some theoretical evolution of price given the accessibility. This gives you a rule making involves some variables related to how much a urban function is going to value the accessibility, etc. So you have a set of rules, each of which can be instantiated with different specific rules from the literature. Okay, so this is the different instances I give you for each of these rules, and I'm going to skip on that, and I'm sorry because this is in French. Okay, once you get this simulation tool with different the possibility to put different rules for each of the rules.
Sorry, I can understand at least one of the rules is that you have a fixed network representing the city.
No, it evolves, but
it's growing.
Yeah, but in fact that's false growth since the shapes it can take through time is constrained by it's not the topology. The final topology is fixed at the beginning of the simulation. It's just that you activate the nodes progressively during the simulation.
But the European ones are not yet, and
those are completely toy networks. In fact, one is a pure grid, and the other one is a radioconcentric shape. And that's I assume that is a really huge hypothesis. Okay. So once again, we want to try to evaluate the trajectory from not only from a final state point of view, but from with the spatial indicators and compare the evolution of these indicators through times with the data. So what we did is that we tried to we choose some metrics to systematically evaluate the simulated developments with really aggregated coefficient like a spatial coefficient of variation of the density of the faces, etc. And typically, for example, when you have when you compare for each set of rules when you executed it on each geometry, okay, geometrical geometry, European geometry and US geometries, and you have you can plot the values of each of your macroscopic indicators, and then you can count both the amplitude of the differences and the order relationship between these indicators. Okay, so what we did for now is to make some. So you see all these rules, and for each of them we have several instances. Okay, so that means a lot of combination of a simple combination of these rules. For what we did for now is just to test a systematic combination, to test all possible combination with a really simple geometry, and to try to see finally if some of this combination of rules allows to generate some multilevel patterns given only the difference of geometry. So those experiments are mainly designed to test the model as a tool and see if we can find this kind of causal relationship, all things about being equal in a really simplified case of this network actually. Okay, but that implies many simulations since these are many instances to test, and there are many agents for each to simulate. So we just make these comparisons through really synthetic indicators. And so, for example, the kind of objects you got, those kind of networks which are the shape is fixed. The activation of nodes is progressive, and so you have a progressive like a densification of power in the center, etc. And what you can look at as indicators, those are these kind of density curves with distance to center through different moments of time. Okay, through the history of you see. And so you do the same for EOS typical grid, typical pattern, and you look at these curves. And finally, what you look at is that the slope of this kind of curves through as synthetic indicators. Okay, so that's where am I now with this project. So that's those are investigations that have to be pursued and completed. I just have a tool for now and something which allows me to tackle questions regarding the impact of the street networks and the speeds of spatial repartition of inside the cities, which could not be tackled with these tools. So I'm glad to have built it. And for now on, I've only tested it on really theoretical and time networks and with theoretical data defined by geographers. So that's not sufficient, and well, that's not satisfactory from empirical point of view. So many work is still to be done to answer the initial question. What we can already say is that for a simple instance of these rules, there exists some combination of parameters that can that allows to render this other relationship between on synthetic indicators like densities, the slope of the density curves of given different geometries. So if you want to read more about all that, you will find some papers at this URL. And so in the perspectives, I plan to benefit from the work on the Louail project, where we try to benefit from the Twitter and from data set to have some realistic map of urban activities and OD matrices and stuff like that. So I hope to benefit from this whole bunch of data to also feed that kind of investigation regarding the long-term evolution of cities. So that's what I had to present today.
I don't understand what is the evolution of accessibility. Are you putting accessibility values according to some historical database, or are you calculating them according to the local density or the change in density, or to what?
Different things to answer that. The accessibilities of each node, in fact, is not issued from real transport database. It is a combination of topological properties which translates the relative accessibility of this node into the graph. So, for example, in the case of this radioconcentric graph, you have the center, which is way more accessible than the multilevel. And in the same time, you see I show you this schema where we show that we inject some parameter values at different moments of the evolutions. Okay, and so for example, what we inject at different combined to this evolution of topology indicators, what we inject are average speed, commuter speed. I'm sorry for my English. At different moments of times, for example, in the case of the European cities, you will have larger values of speeds on outer rings than on inner ones for the last decades. Because you know from transport surveys that the average speeds in the suburbs of the European cities is higher than the centers.
Yeah,
so there is
but I mean, I was thinking that usually when some city grows, usually the periphery is very badly communicated. When it grows, the periphery is no longer the periphery, it becomes something in between, then you have more public transportation, more roads, and so I guess that there should be some coupling between the average speed and the accessibility with the density and the kind of activities that are there.
Yeah, in fact, you're right, and that's totally agreed, since we take into account this the impact of the congestion on accessibility through these values of average values of speed that we inject into the models for different parts of the graph, given time evolution. That's right. For example, I don't want to enter into the detail, but for example, when you see when city grows, the speeds goes lower in the suburbs. In fact, that depends. For example, the periphery to periphery speeds are with transit public are generally really poor. But at the same time, the speed from the periphery to the center increases with development.
Well, it was just about you said the mean speed of the commuters was different in the US and in Europe. I mean, why is that? And then which one influences which one? Because I guess when the city gets bigger, then you are also to have some mean of transportation that you need more speed, and then in return you also have some feedback on the growth of the city.
Well, there is some historical reasons to that, which are really obvious. Is that for European cities, for example, there are real cities, and the centers they've been built in the village, so they are really not adapted to the use of personal cars inside the cities. And so when you look at the average speed, the average commuting speed with personal cars in the European cities, it's generally very low because the roads are not large and
the mean speed was personal cars or was all mean of transportation?
Well, in the case of the survey for the Ile-de-France study, it's an average between it's a ponderated average between the number of people which take public transport and public transport. But in the US, for example, public transport is very marginal, and the speeds are kind of good because well, for example, for the I don't know, for Los Angeles, Phoenix, and all cities from the West Coast. Those have been built, let's say, from the beginning of the 20th centuries, and sorry, I don't get the streets, the roads were clearly designed in order to be like ours, not in the field. So, for the second part of your question, which was
well, because you, as far as I understood, you use it as a sort of forcing mechanism of the city. But sometimes it's also driven by the size of the city. You don't know which one drives which one.
Yeah, this is related to what you just said about this. This is a huge simplification. I agree, and this interaction, this feedback interaction is surely taken into account. But once again, given that for now we didn't have even this it's complicated because when you consider a historical period, you have so few data for before, let's say, I don't know, not for population database, we have some data given the census, which we have for very ancient period of times, but apart from this population data, you don't have a lot of sense. There are some works that have been done recently by, for example, validity, which is in the IFISC project, is an historian of Paris, which is kind of interesting since they have numerized the street networks of Paris for since the middle of the 18th centuries, and so they can simulate growth given the real street networks. But that kind of historical databases of street networks for different cities is still rare, and I hope it's going to become it's going to be soon available more